Hi class, it's Mr. Maltzby. As you know, we don't have school, and we'll. I don't, oh, my microphone fell over. I don't know when we'll have school again. Oh, there I go. Okay. I didn't have time to make a vlog. I started to, and then I had some trouble with my Apple ID, and it's also 2 o'clock now. So if I don't finish the video and get it up by 3, I feel like I haven't held up my end of the bargain. So here we go. Let's get front and center here. This is the last time you're going to see me today, except maybe at the end. We are doing 4 things in this video. Thing number 1, we are going to quickly talk about the point of the video. Maybe that'll take 30 seconds. Thing number 2, I'm going to go through the answers to the BV homework. And I'm going to go pretty quick. So if you haven't done the BV homework, I want you to at least pause it and read every question. You don't have to come up with an answer for every question. But I am not going to kind of stop and read questions. I'm just going to show my answer and then maybe talk about 1 or 2 kind of things about the problem. But none of it's going to be a full explanation of every problem. So this part, if you actually want to understand the homework, you got to stop and read it. Or just be prepared to kind of stop the screen and read the question right before I start talking. That'll work also. So purpose of the video, go through the BV homework. Then go back and actually get into today's lesson, which is proving the fundamental theorem of calculus. We've already kind of we've kind of talked about fundamental theorem of calculus, but we're going to talk about what it exactly is and prove it, and that's going to be the meat of the video. And then also I'm going to go through and do the AV homework. And none of you should have done the AV homework yet, so the right way to do it is to hit pause or stop the video and take a break and then maybe do the AV homework and then finish the video. But if you're just watching this all in one sitting, when I go through the homework, it doesn't make perfect sense one way or the other. You got to hit pause and read along, or kind of stop the video and go do it, or just accept that you're going to be a little bit lost. I don't mean that in a bad way. It's okay to be lost. All right, I'm done talking. Let's go to number 1, purpose of the video. Say goodbye. This is not the purpose of the video. This is the purpose of the video. F equal G prime. This is something we've kind of been saying. What today we're going to do is do the proof of it. We did observation. We noticed that if you make this graph of G, G represents the integral of F, but F kind of represents the derivative or the slope of G. That there's a two-way relationship. G is related to F by keeping track of area, but F is related to G by keeping track of slope. So for example, anywhere G had a maximum, the Y value of F had a positive to negative sign change. Or anywhere that G was a decreasing graph, so a negative slope, F had a negative Y value. And that allowed us to label this. That was just observation. It wasn't proof. All we were doing was noticing a connection. What we're going to do today is some blue notes, so the steps of the proof you don't get quizzed on. But really everything in this class is fact, right? We never do things just because they feel like they work. We always want to prove them as a fact using all the tools we've learned this far. All right, done with thing number 1, which is today we're going to talk about F equal G prime. Let's do the homework, the BV homework. And like I said, we're going to go pretty fast. So question 2 could have been on the quiz. It's actually a lot like the last question on page 3. The trick for question 2 is you do not add 1 to the integral of F. Instead, you must add 1's integral value. You got to take f of x plus 1 and break it into an integral for f of x and an integral for 1. And if you integrate 1 from -3 to 3, it's 6. Because it is 1 tall and 6 wide, and 1 times 6 is 6. So that was kind of the trick to that one. Where I got the -2 from and reading the problem, something you got to do on your own. But that's the trick for that one. Number 3, we're asked to find a total change in altitude, which means we got to integrate a rate of change. And then to know what the limits were, we needed to look when the rate was negative. So when you integrate a rate, you get total change in altitude from A to B. And I graphed the rate function to get that the A was 1.572 and the B was 3514. Okay, other BV stuff, graph 5. We're told g is the integral of f. So we right away go up to this graph of f and write equals g prime. We just do that now. And what we've basically done there is use the fundamental theorem of calculus. We haven't proved it yet, but we're already using it because we've noticed that it's true. And then the rest of this, once we do this, the work is easy. Which g is the greatest? Well, greatest means maximum. And maximums occur when derivatives change sign plus to minus. And in this case, derivative of g, that's the same thing as f. So let's just look for that plus to minus in g. And so g of 1, right? G of 1, that's a plus to minus for f, so that's a plus to minus for g prime. That's going to be a maximum for g. And then this is my explanation 2. I'm not going to get into it. Hit pause. All right, some of you hit pause, some of you didn't. We're moving on. Number 6 was Ace Ventura property. 5 to 2 is backwards. So if you got negative 21, it was wrong. You needed to take 5 to 2 and flip it, which means we're going to do the opposite of negative 4. It ends up being positive 4, and we wind up with negative 13 as our answer. All right, we're skipping that whole page. And then the last bit of the BV homework. G of 4 and G of 6, we're just doing areas. Area from 0 to 4 is 8. Area from 0 to 6 is going to be positive 8. Negative 1 comes out to an integral value of 7, right? So 1 is a positive area, but we subtract that amount. So 8 minus 1 makes 7. And then here we're just, oh, look at this. F equal G prime, right? We just do that now. So when it says find G prime, it's basically saying find F. So G prime of X, F of X, same thing. So G prime of 3, F of 3, same thing. Let's go to the graph. F of 3 is 2. If F of 3 is 2, G prime of 3 is 2 because F and G prime are the same. And same thing here. G prime of 6, well, that just means F of 6, right? If we label this graph, we can translate these questions, and these questions become easy. G prime of 6, that's F of 6. F of 6 is 0. There we go. And same thing with the rest of the questions. When will G increase? Well, whenever G prime is positive. When is G prime positive? Well, G prime is F. Hey, look, this is when F is positive. So 0 to 4, also 6 to 7. Number 4, G relative minimum. That's going to be G prime sign change. But a G prime sign change, same thing as an F sign change. So this labeling right here is making all these questions easy. X equals 6 is our negative to positive. What is this value? Well, G of 6, we actually already did G of 6. G of 6 is 7 up here, so G of 6 is still 7. And then I didn't assign number 6, but let's talk about it. What is the absolute minimum value of G? A relative minimum value is 7. 7 is the relative minimum value, but it's not the absolute minimum value. If we actually look at the endpoints of G, not F, but G, G of 0, well, G of 0 would be the integral from 0 to 0. And the integral from 0 to 0 is going to be 0, right? That's one of our properties. I'm pretty sure that 0 is less than 7. So this endpoint is less than this relative minimum. This endpoint is the absolute minimum, right? Sometimes absolute extrema are endpoints. Okay, that was the BV homework, and I know that was fast. But the BV homework was a combination of two things. Questions similar to the quiz, and questions based on relabeling graphs and then just using what we know about derivatives to answer questions. Okay, let's go ahead and look at our point. So once again, our point is to talk about F equals G prime. In other words, our point is to, nope. Okay, well, let's see here. This is a graph of A. So A prime, that should be little f. That's kind of the point. Oh, yeah, here we go. Graph of f, that's graph of A prime. Really, it's this, though. You don't need to copy this down. It's at the bottom of the worksheet. See how I skipped all this that we didn't do in class? You can skip over that. I think we left off right here. These are skippable questions. They really are. This is the fundamental theorem of calculus. That if it's not that these functions exist. It's not creating a scatter plot that's the fundamental theorem of calculus. It's that if you create this function, recognize that big F's derivative, or what I was calling A up there, big F's derivative, that is little f. So if big F integrates little f is big F prime, right? It's that labeling of the graphs, that A prime was little f, that G prime was little f. or in this case, that big F prime is little f, right? What we're going to do is go through and prove that. We're not going to use it. We're just kind of going to prove that it's a true statement. So at the moment, we are making these labels because it seems to be a thing, or maybe it was just because I told you to, right? If some of you didn't get it, I just said, hey, start labeling this now. So let's look at why it's true, not just because I said so. All right, here's today's class. Oh, lots of stuff. Let's talk about this graph. This is the graph that we're going to use for today's class. It is a graph of little f, and I have marked some places on the x-axis. I've marked this place x, and then I have marked this place x plus h. So if we're going to call this x and we're going to call this x plus h, what that means is that they are h apart. H is the difference between them. You take x, you add on h, gosh darn it, you get x plus h. All right, the first area we're going to talk about in this graph is the red. Look at all that red, right? And if I ask you to find the red, we're going to call it a of x plus h. Finding the red would mean working out the integral value starting at 0 and ending all the way on the right side at x plus h. So I hope just, hit pause if you need to process the idea that all of this red is represented by this integral. Does that make sense? 0 to x plus h? Okay, good. Let's talk about the blue. Blue is not so much, so we're going to still start at 0, but we are going to end up with a different upper limit. We're going to stop at x. So the blue, let me go back. I just want to stress that we're going to call the red a of x plus h. A is the integral, so a of x plus h is the area up to x plus h. The blue is the area just up to x, so we're going to call it a of x. It's the integral from 0 to x. So that's the blue. And the last thing we're going to talk about is the green. I want you to watch this. There are a couple of ways to think about the green. You could think about the green as from x to x plus h, in which case we would put x at the bottom of the limit because that's where the area starts, and we would put x plus h at the top because that's where the area ends. So we could think of it as all of this, but we could also think of it as the red minus the blue, right? If we take our red, subtract our blue, we wind up with our green. And this proof hinges on the fact that we should be able to agree that both of these are true statements, that the green is equal to the green, that this integral value would be equivalent to whatever you get when you do red minus blue. If we accept that as fact, we're going to be able to prove the fundamental theorem of calculus. And we should, right? I mean, this is fact. This area, it totally is this minus this, and it is also this, right? Those are both facts. So we're ready to proceed. So first thing I'm going to do here is I'm going to take out the words red and the words blue and replace them with symbols. So the red and the blue, right? This integral was the red. This integral was the blue. This integral is the green, so that's our green. And over here we have our red minus our blue. And then what I'm going to do is take those integral symbols and use the function notation for them. So this was a of x plus h. This was a of x. That was the notation that we assigned to those integrals. All right, let me kind of scroll down and make sure I know where we're going. Okay. Let's talk about another way to measure the green besides the red minus the blue and besides x to x plus h. We are going to measure it with the purple. Here's the purple. The purple is this new region. It's a rectangle that I've drawn. And what I have done is I have put this symbol in here. Gosh, I hope we can agree that the green does not equal the purple. So the green, so x to x plus h, f of t dt, that is not going to be f of x times h. Let's make sure we agree we know where this comes from, that if this is a rectangle, it's got a height, and its height is the f value at x, so its height is f of x, and it has a width, and if it's from x to x plus h, its width is h. So we're looking at height times base, two sides of a rectangle. But gosh darn it, the purple, it doesn't equal the green. But that's okay. For the moment, we don't need it to equal the green. What we just need it to do is approximate the green. So we're going to take this screen and we're going to get rid of this does not equal and just replace it with approximate. After all, rectangles was how we began approximating actual area in the first place. So I've just taken out that does not equals and replaced it with approximate. Now, I have used a really loose symbol because I hope we can agree that, I hope we agree this is a loose approximation. I drew these big lines on purpose. This kind of big curve represents that this is not a very good approximation. On the next screen, we're going to look at a better approximation. So what I've done here, let's make sure we noticed. I have taken h and I have shrunk the value of h, which has brought x and x plus h closer together. So all the concepts still hold, right? That if you did the entire area and subtracted all of this, it would get you the green. But also, if you found the area of the purple, it would estimate the green. Now, if we compare the two, if we compare this estimate to this estimate, I hope we can agree this is a better approximation. So what I'm going to do here is just kind of take this approximate symbol and change it to something a little less dramatic. All right. Now the green is approximately the purple. Yeah, they're a little bit closer, so we're using a little bit better symbol. But it's still an approximation. This is still a rectangle, and this is still not. Well, if we wanted an even better approximation, what we should just do is make the distance from x to x plus h, so make the value of h smaller. The smaller we make h, the closer the green gets to the size of the purple. And since the green and purple are getting a little bit closer, let's switch our symbol. Now we have something that's not very dramatic, right? These are more or less pretty close to the same. So we're using a symbol that's getting closer and closer to the equal symbol. We started pretty far away from equal, so I started pretty far away from the equal symbol. But the closer and closer we get to these matching, the closer and closer we're going to get to the equal symbol. Now, what would it take? Oh, I'm sorry. Here, last thing I'm going to do is take the green and replace it with that function notation that represented red minus blue. So a of x plus h was red, a of x was blue. So I'm just switching from the integral symbol to the function notation. But it's still a representation of the green. I'm actually making a substitution. Okay, question. We want to use the equal symbol. At the moment, we are not allowed to use the equal symbol because obviously the amount of green does not equal the amount of purple. And please remember that the green is like all the way down, that the purple is covering up some of the green. The green is the full area all the way down to the x-axis, and the purple is the rectangle on top of it. I want to use the equal symbol, but they're not equal. So here's my question. As h gets smaller, this gets closer to equal. How big should h be if they're exactly equal? The answer is 0, right? H should be as small as possible. That's calculus. All right, I wish I hadn't done that. That was corny. Yeah, so we know. Oh, I jumped the gun on something. And what we're going to do before we proceed is we're going to take this potential equation and do a little bit of manipulation. We're going to take this h that's multiply on one side and just bring it over with old school algebra so it's divide on the other. So we're going to divide both sides by h. And over here we have a of x plus h minus a of x over h. And some of you, especially the sophomores, might be recognizing this symbol or where we're going with this. All right, we want these to be equal. We need h to be equal to 0. You can't actually just plug in 0 because then you're dividing by 0. So what we need to do is take the limit. We're going to take the limit as h approaches 0 of a of x plus h minus x over h. That is going to squeeze this so small that the amount of purple becomes equivalent to the amount of green. And what happens is that equation that started with a big approximation symbol in it can now just be written with an equal symbol in it. And we've actually done our proof. You may have forgotten what we were trying to prove. We were trying to prove that if a is the integral of f, then you can just label this graph. You know what? I hadn't planned on doing any live drawing, but let's do it. Our goal is to be able to label this graph equal to A prime with some mathematical reasoning. Not just some observation, but some actual hard math. And that's what we've got right here. A prime, I don't know if you remember, but this right here is what we call definition of the derivative. This is how we started with derivatives. To write out the meaning of a function's derivative meant to write out this symbol with the limit, with the 0, with the x plus h, or the x and the divided by h. So why don't we go ahead and proceed to our next slide. Proceed to the next slide. Sorry. So this symbol is just the symbol for A's derivative. So we're going to take out this big expression and we're going to replace it with A prime of x. And we have now proved what we wanted to prove, right? That was our goal, is to say that little f is equal to A prime and say it with some mathematical reasoning. And how we got there was starting with a couple of different ways to measure the area, bringing in that third concept of approximation, and then saying as h approaches 0, the approximation approaches the actual value. And what we actually managed to do was create the definition of the derivative symbol along the way, just using some common sense and some algebra about how the areas work. All right, so that's our proof. I am not, on a scale of 1 to 10, this video was a 6. But as your reward, we're going to go through and do the AV homework. Remember, this is all you got to know right here, that A prime is f. And what we did was we proved that it's true. So let's go, let's see, where do we want to go now? Let's not go there. Let's go here. So we basically proved that this is true, that if big F integrates little f, big F prime of x equals little f of x. In the video, I was using A. I was using an A right here, which meant we used an A right here. But we'll see a lot of big F and big F too, capital F. All right, let's go AV homework. There it is. So I hope you all agree that G will decrease whenever G prime is negative. So if G integrates sine of t squared, who is G prime? Sine of x squared. So this is what makes this different is we actually have a specific function written in here. In the video, or I'm sorry, in class, we would just have like little f. So then we would say G prime is little f. Well, now that we have an exact function given, we just want to say that G prime is that exact function. The only difference is we take out the t and replace the t with an x. So instead of calling it sine of t squared, we call it sine of x squared. And the reason we want to do that is because if g of x is a function of x, we want to express g prime of x also. If x is the independent variable for g, we want to use x as the independent variable for g prime. So we're going to do a little switch of letter. We're going to stop using the t and start using the x. Actually, I believe I forgot to answer this, but here's what you're going to do. You're going to graph sine of x squared in your calculator, because sine of x squared is the g prime. And whatever this g prime is negative, this g will be decreasing. That one we already did. Okay. And so here we go. Basically, what we're doing is saying this function integrates this function. Who is y's derivative? Well, whatever you're integrating, that's the derivative. So we just rewrite that expression, that the derivative of y, that the y prime or the dy dx, that's just whatever you're integrating. In class, we would have notation in here like little f. But instead of calling it little f, we're going to call it sine of 4t. So instead of calling y prime little f, we're going to call y prime sine of 4x. So we're just rewriting the integrand, taking out the t, plugging in the x. Same thing down here. We got to find dy dx. Before we do that, we're going to flip the limits because x to 3 feels backwards. We want it 3 to x, so we're going to put a negative in front. That's that red negative. So what is the derivative? Well, we're going to take our integrand, and we're going to call that the derivative of the integral. And don't forget about that negative, so it's negative cosine x. And then our last one right here, I'm going to highlight. So first we're going to rewrite x to 6 feels backwards. So instead of calling it minus, let's call it plus. Let's change the sign, use Ace Ventura property, and that makes it go 6 to x. And now we're just going to take the derivative of this. The first term is normal calculus, so the derivative of sine x is not complicated. The derivative of sine x is cosine x. So the blue goes with the blue. The derivative of the integral, well, the derivative kind of undoes the integral, leaving us with cosine. And what we do is we take out the t, we replace it with an x. So the derivative of the green term here is the green term over here. It's just the integrand with an x in place. All right. And I think that covers all of the homework, right? Yep. All right. Let's bring it back here. Where's my FaceTime? Okay. I'm not sure how long the video was, but it was a little hectic. It's hard to do a proof from your bedroom. But here's the nutshell version. The f equal g prime thing, there's some mathematics that proves that it's a fact. And that mathematics is just based on measuring a space a couple of different ways that make sense and being able to manipulate the symbols until you reach that kind of limit as h approaches 0 place, because that represents definition of the derivative. So it counts as proof instead of just kind of noticing that it's true. If we don't have school Thursday, there won't be a video for that. If we don't have school Friday, and I don't see you till Monday, there'll be one more video. I will put it up Saturday at noon, or by Saturday at noon. So just so you know. So if Wednesday, Thursday equals one video, Wednesday, Thursday, Friday equals 2 videos, I kind of hope I'll see you Friday. All right, bye-bye.